All right, you guys, so we're going to start with bomb calorimetry this week. This is week 2. Last week we talked about coffee cup calorimetry, so we're going to move on. Remember that your homework is listed on the first slide of the PowerPoint. There is a question from Chapter 9, and those page numbers for Chapter 9 are on your Canvas assignment page, so you can check that out. Okay, so bomb calorimetry is a little bit different of a setup than coffee cup calorimetry. It's a lot less exciting than it sounds. Instead of looking at heat exchange at constant pressure, we're at constant volume. We're still observing a temperature change where a reaction happens, or, you know, when we did coffee cup calorimetry, it didn't even have to be a reaction, but something happens in your calorimeter. There's a change in temperature somewhere, and we were at constant pressure before because it was just atmospheric, but in a bomb calorimeter, we're at constant volume. And I'll show you a setup for a bomb calorimeter. Essentially, we're doing a combustion reaction in a small vessel, so you're going to create a lot of pressure, so that's why pressure is not constant, but your volume doesn't change because it's in a little reaction chamber. So here, your delta E is going to be equal to your heat at constant volume. Okay, so that's what we're going to be looking at. Here's your bomb calorimeter setup. You have your little reaction chamber here, okay? Here's your constant volume. It's just in there. Your pressure's gonna change. Here's your, your ignition wires. That's what sparks the reaction to happen. You stir this water that's in your calorimeter and you measure temperature change. These reactions are going to be exothermic because they're all combustions. I've done one of these. It's not very exciting because you can't really see anything. So that's what it is. Here's your equation. It's pretty simple, you guys. You're going to be given, this is your heat capacity for your calorimeter. And we have a delta T, which we had before, which remember is T final minus T initial. And we solve. That's it. All right. We are going to have to solve in terms of, usually it's kilojoules per mole. So again, we're going to have to calculate moles. So, but other than that, it's pretty simple. Here's our bomb calorimeter calculations. There's a little star here, I think, because mastering, I think that was my note that mastering has a good video for this. So you can also see this on Mastering Chem. All right, so sucrose reacts with oxygen according to the following reactions. So here's our sucrose. We are burning it in the presence of oxygen. Anytime you have a combustion, you make carbon dioxide and water. It's all balanced for you. We calculate the heat produced per mole of sucrose, per mole, so that means we have to find moles. And we do that by converting 2.75 grams to moles using the molar mass of your sucrose, and we're combusted with excess oxygen in a bomb calorimeter. Cool. The temperature change, oh look, we don't even have to calculate it. They already did T final minus T initial for us, and there's our delta T. Here's our heat capacity of the calorimeter, so that's big C. I don't have a ton of room here, but we're gonna do the best that we can. So I'm gonna say Q is gonna be equal to big C delta T. All right, and then I find moles. All right, so big C delta T, we're gonna say my big C is 2540 joules per degree C. That's my heat capacity of my calorimeter. And then I'm gonna multiply that by my temperature change, which we didn't have to calculate. They just gave it to us because they're super nice. All right. And that gets us 5105.4 joules. Degree C has canceled. So that's my Q. Now all I have to do is divide by my moles. In order to find moles, I'm going to do this up here where I have a little space. I have 2.75 grams of sucrose, C12H22O11. So I need to go to my periodic table and I need to find what my molar mass is for sucrose. And then I convert. Carbon has a molar mass of 12, so 12 times 12 144. You add the hydrogen. So the molar mass of hydrogen is 1. So you're going to multiply that by 22. So that's just 22. And then we have 11 oxygen. The molar mass for oxygen is 16 grams per mole. So you're going to multiply that by 11. And you add all those numbers up together, and we get 342 grams per 1 mole. All right. I know that grams go on the bottom because then I can cancel. When I do this, you're going to get a really small amount of moles, and that's totally fine. We have, 0.008 moles. So I take my Q. I'm going to divide by 0.008 moles. So my answer is, it's negative because I have to change the sign. Negative 638 kilojoules per mole. I converted from joules to kilojoules by dividing by 1,000. And this is my final answer. It asked for per mole, so I gave it per mole. You could also report it in joules because I didn't specify what I wanted it in. You just need to remember your negative sign because it's exothermic, because it's a bomb calorimeter, and we have to change the sign anytime we are calculating Q. That's that. Okay, internal energy. So this equation, you are going to need to know, well, you'll be given it, but you need to know how to use it in order to find all the different variables that you could be given. Delta E, remember, is our internal energy. This is just the heat enthalpy or heat energy. And here's your work function. All right. What this equation is telling us is that the difference between enthalpy and internal energy is really small, because this work function, work is usually a really small amount and can usually be ignored. I'm going to say usually small. The difference between enthalpy and energy is usually small. And so a lot of the time, what we do is we kind of ignore work and we just focus on the enthalpy. And we consider that the total energy of the system. All right, so all we want to do is remember that delta E is going to be basically Q plus W, right? And delta H is going to be Q over mole. So we just need to figure out what the energy and enthalpy are for this equation. So here's my Q. It produces, which means it's exothermic, so that's negative. It does 3 kilojoules of work, so that's negative. So if I'm finding my energy, I'm going to take negative 2658 kilojoules, and I'm going to just add my work, negative 3 kilojoules. All right, that gives me, if you add those up, negative 2661 kilojoules. Okay, and then I'm looking for Q over mole. So again, negative 2658 kilojoules. I have 1 mole, it tells me that. So my delta H is negative 2658 kilojoules. So as you can see, the difference is really, really small. So a lot of the time from now on, we are just going to talk about delta H, and we can kind of ignore delta E because we can kind of ignore work. It's pretty insignificant for what we're worried about, especially during really small chemical processes. So let's look at calculating enthalpy, delta H, in 4 different ways. The first way is looking at our bond energies. So how much energy is stored in your bond. And we need to break bonds, which is gonna cost us energy. And then we form bonds, which gets us energy out. So we need to figure out if overall, are we spending more than we're making, or can we get out more than we've put in? This is section 910 of your book. The pages, like I said before, are on your Canvas page, so you can check it out there. You might want to review doing Lewis structures. I know, nobody likes Lewis structures, but if you go back and review those, you'll be good. Stoich we got to use stoichiometry of a reaction in order to determine how much energy we're getting out. It's just, if you put in more, you're going to get out more, right? So if we put in more stuff, and then that means that we're going to get more energy out, or have to put more energy in. All right, so Hess's law is sort of a puzzle. We're going to use the enthalpies of known reactions to solve for an unknown. And then enthalpies of formation, this is tabulated values that we just have to find and just use some math to calculate the enthalpy of a reaction. So let's start with some bond energies. This is a table from chapter 9, page numbers are there, table 9.3. When we break bonds, it costs us energy. We have to put energy in order to break a bond. When bonds are formed, we get energy out. We need to calculate overall if our bank account, if we're spending more than we're making, if our bank account is positive or negative. Have we needed to put in more than we're getting out, or vice versa? So this is going to tell us what my overall enthalpy for these reactions are, and we just have to break it down and look at the actual chemical structures of each product in each reactant and kind of go from there. I've taken the values from this table and I just copied this over. Here's my example. For every carbon-hydrogen bond, we're going to get 414 kilojoules per mole, either out or we'll have to put it in if we break it, right? And then chlorine-chlorine bonds, here's the value, and so on and so forth. All right, so I just set it up so that our bonds that we are breaking are on our reactant side and the bonds that we are forming are on our product side. When you form bonds, you get energy out, okay? Energy out because they're forming. That's energy flows out. So you need to remember that these values have to be negative. You need to switch the sign and then we can add when we're done. Okay, so let me show you what we're gonna do. I'm gonna take methane, CH4, and I'm just gonna draw my Lewis structure just so I can see how many bonds I have to break or form. I'm gonna add chlorine, which is just ClCl. Okay, now over here, instead of methane, there we go. I think that's chloroform, if I remember correctly. And there's hydrochloric acid. If we look at methane and chloroform, I have to break one carbon-hydrogen bond. And I form one carbon-chlorine bond. I also have to break a chlorine-chlorine bond, and I form a chlorine-hydrogen bond. So when I do my math, I'm going to say 1 times 414 to account for my carbon-hydrogen bond that I broke. And I need to add a chlorine-chlorine bond. 1. If there was 2 of them, I'd just put 2 times 243 kilojoules per mole. Okay. So I add those up, and I get 657 kilojoules per mole. Now, I have to figure out what I've formed. So I have 1 times CCl, negative 339 kilojoules per mole, plus, again, there's only one of them, 1 times negative 431 kilojoules per mole. All right, so then I add those up and I get negative 770 kilojoules per mole. It is negative because these are the ones that we're forming and we get energy out. So I add them up to see what, am I going to come out in the positive or in the negative? This gets me an exothermic process, which is good because that's downhill. I don't have to put energy into it. Kilojoules per mole. And that, my friends, is my delta H. That's my answer. Okay? The hardest part about these problems is figuring out your Lewis structures. So that's what you got to review. Let's look at 9.2. All right, here's problem 9.2 all solved out for you, so I'll quickly walk through it. I drew my Lewis structures for methane, for water, and there are 2 of them, so I drew 2. There are 4 H2 atoms, so I drew 4 of them. There we go. And there's 1 CO2, so I drew 1. There's a special value for a carbon-oxygen double bond that's in CO2 that's different than the one that's in the main table. It's like in a little asterisk at the bottom of the table. So if you're wondering where I got that number, that's where it came from. So I broke all the bonds that I needed to break, and I formed all the bonds, and I circled all the bonds that I needed to form. So all my CH bonds had to break. Each of my OH bonds had to break. I formed 4 HH bonds, and I formed 2 COO bonds. So down in the bottom in the red is my broken bonds. And I needed 4 times 414 for each carbon hydrogen bond, and I did the same for OH, and I got the value of 3512 kilojoules. So that's how much I had to put in order for those bonds to break. When I form my new bonds, I get that energy out. So I do 4 times 436, 2 times 799. I have to make my 3,342 kilojoules that I get back out. I have to make that negative because I'm getting it out. It's exothermic. It's coming out of the reaction. And so that's the negative one. So I add them up at the bottom in very pretty colors, and I get a net of plus 170 kilojoules. So that's my delta H per mole of my combustion of methane, or reaction of methane with water. So there it is. That's how you do those problems. All right. So there's a homework problem that's based on that. You can look that over. And that's our first way to calculate delta H. So now we're going to go into stoichiometry. Remember that stoichiometry is just how many atoms are reacting in each equation. So my stoich is going to be the numbers that are out in front of your reactants and your products. So in this case, I have my 4. If there's no number, it's just 1. And I got 2. All right, that's my stoichiometry. So it depends on how much, the amount of my reactants. Okay, so it says the enthalpy for the formation of sodium oxide is shown below. Here is you will be given your delta H, or you'll be given a mass and you'll have to convert to delta H, but either way, you have to be given one of them. So part A asks, what is the amount of heat released when 1 mole of Na2O is formed? Okay, so when I have 1 mole of Na2O, okay, I have to look, and what I'm going to use is I'm going to use my delta H as a conversion factor, but I need to figure out how many moles of my sodium oxide, how much are reacting or being produced for this 828. So every time this reaction happens, I produce 2, if you can even see it anymore, 2 moles of Na2O. So this amount is per 2 moles of sodium oxide. Okay, so now I use this number as my conversion factor to convert. So I put my 2 moles here, because now that cancels. And up top I have my negative 828 kilojoules. I do 1 times negative 828 divided by 2, and I get negative 414 kilojoules out. And that is the amount of heat released when 1 mole is formed. The trick is to just use the stoich and pair it up with your delta H to use this as a conversion factor. Okay, so you'll always be given delta H. You'll either be given an amount or an energy, and you'll have to convert back and forth. So in this case, we were given a mole. If you're given, like let's say I was given grams. In that case, you would have to convert from grams to moles and then go ahead and solve. All right, so part B. Here's now we're given an amount. What is the amount of heat released when 6 grams of Na is burned? So same equation, so I'm going to write this here. 4 Na plus just O2 goes to 2 Na2O. My delta H is the same, negative 828 kilojoules. All right, pause. We got to convert grams to moles and then moles to kilojoules. Give it a try. Okay, there's your answer. All right, 6 grams, we convert to moles. We convert grams to moles using the molar mass. Then you use your delta H that you're given. There are 4 moles of Na in this reaction, so you throw that on the bottom. 6 times 1 divided by 23 times negative 828 divided by 4. Done. All right, that's stoichiometry. Okay. Here's another one, number 19. I want you to give this a try. There's your answer. Just check, make sure it all makes sense, and that's stoichiometry. All right, next, Hess's law. These are like puzzles. So we are given an equation and we don't know what the delta H is. I don't know. And we can't figure it out by measuring it. So what you can do is you can take equations that have all of the components of your goal equation in them and twist them around and manipulate them in order to get what you're looking for. And I'll show you an example and walk you through it so that you understand what that even means. So the rules for utilizing Hess's law to solve a problem. If an equation is multiplied by a factor, let's say you have to multiply your whole thing by 2, you also have to multiply your delta H by that same number, or divide if you wanted to divide. But any mathematical operation that you do to the equation, you must do to the delta H number that you're given as well. If you reverse a chemical equation, you must reverse the sign of delta H. And when you add up the series of steps, the sum will be delta H for the overall reaction. Okay. So, in this problem, here is our goal. This is the equation that we do not know the enthalpy for, and we want to figure it out. Since we cannot measure it, what we are going to do is we are going to use the 3 equations A, B, and C that we're given, and we're going to flip these around and manipulate them so that at the end, when we add them up, they're going to equal our given equation, and then we can do the same thing with the numbers. Okay, so what I like to do first is, okay, I can color code. I'm going to box in all of my reactants. Now I'm going to go on a scavenger hunt and I'm going to find them below. So there's a carbon, and here's my water, and the stoichiometry doesn't matter right now, so who cares about that number out in front for now. Okay, so now I'm going to circle, and I can do it in green, my products. So I'm looking for CO. Here's CO and H2. There we go. Okay, so now I've identified everything that I need to keep and not cancel out because they're in my goal equation. Everything else I'm gonna have to cancel out. So that means that I need to get rid of CO2 and I also need to get rid of O2. The way that you do that is by having them on opposite sides of the arrow, and then you can cancel. If I have 2 carbon dioxides on one side, I can have 2 carbon dioxides on the other side. I'm going to take the first equation and I'm going to see if I need to flip it around. By flipping it, my reactants would become products and my products would become reactants. With A, I don't have to do that because my C is on my reactant side and that's where it needs to be. All right, so what I need to do is I need to flip. I need to learn how to spell. There we go. I need to flip B because CO is on the reactant side and I need it on the product side. I need it on the green circle side. I also need to flip, oh my goodness, there we go. I also need to flip C because that's going to fix my water issue as well as my H2 problem. So what I'm going to do is I'm going to write a little squiggle and I'm going to copy everything down so that I can keep track of everything because it is difficult to keep track of all this stuff. Okay, I'm going to flip. What that means is I write 2CO2 arrow 2CO plus O2, and I need to flip this sign. So now my sign is positive 566.0. All right, and then C I also flip. So 2 waters goes to 2H2 plus O2, and my sign flips again, 483.6. Okay, so now I have done my flipping. Now I got to get rid of the things that I did not box in. So if I look above, all right, so let's find CO2 in orange. So CO2 is here and CO2 is here. So I can cancel it out because it's on opposite sides of the arrow. However, I have 2 here and I only have 1 here. So what I need to do is I need to multiply this whole thing by 2. In order to make that work. Okay, so I'm gonna copy that one down here. So I'm gonna write, so I got 2C plus 2O2 gives me 2CO2, and I have to multiply 393.5 times 2, which gives me negative 787. All right, and now I am gonna cross this out so that I don't get confused and use it. All right, so here I am. All right. The other thing I need to get rid of is oxygen, right? Because my CO2 now, that matches, so we can cancel that out eventually. So now I got to check my oxygen. I have 2 O2s on this side. So here's an O2 and here's an O2. That's 2, and I have 2 here. Oh, great. So that balances out. So I can cancel one of these with one of those and then the other one here. And then my CO2, I can cancel like that. So now I'm going to bring down what I have left. And we'll put that red. So I got 2 carbon plus 2 H2O gives me 2 CO, because I'm just bringing down whatever's left, plus 2 H2. And now I add up these numbers. So I take 566 plus 483.6 plus negative 787, and I end up with 262.6. Okay, great. Now I have to go up to my goal, and I have to see if they match. And they don't, but I can make them match because I have 2 carbon, 1 carbon, 2 waters, 1 water, 2 COs, 1 CO, and 2 H2, right? So everything's doubled. So what I do is I just take and I divide everything by 2. All right? What that does is it gets rid of my 2's once I divide it, right? So now it matches. And my final answer is 262.6 divided by 2, which is 131.3 kilojoules. And after all that, this is my answer. That's the only thing I care about, is that number there. So now this looks like a big old mess. But when you flip the sign. So I flipped this one, right? Flip. So my sign changed. I flipped this one, so my sign changed. This one I multiplied by a factor of 2 in order to get rid, because I had like a CO2 problem, right? So that became this guy. So now everybody had a 2 out in front, which then I could get rid of my CO2. I could get rid of my 2 oxygen because I had 1 here and 1 here. And I had 2 on this side, so I could get rid of all of those. I carried everything down, but then I had to divide by a factor of 2 to make it all work. Everything I did, I had to follow through and do with the numbers. So that's Hess's law. And this is a big mess. All right. So here's number 20. I want you to try 20, and then I want you to come back and check your answer. All right, so here's the solution for 20. Hopefully it made sense. I think the biggest thing that people get confused about is why I did the multiplication of B, why I multiplied by 3, and I did that to get rid of CO2. And then I multiplied C by 2 because I had to get rid of H2O. And it all checks out in the end. So there's that one. Take a look, see what you got. All right, and 21. So what we need to do is, we don't have a goal equation, but I'm going to write it out for you. This is the combustion of 1 mole of ethane. So your goal is going to be your ethane, C2H6, plus, it's actually 7/2 O2 if you simplify to 1 mole of ethane, 2 CO2 plus 3 H2O. So there is your combustion of 1 mole of ethane. There's your goal. Here are your ABC. All right, so try this one. All right, the last type of problem for this chapter is calculating your enthalpy of a reaction from standard enthalpy of formation values. So what these are is they are tabulated values that have been studied, and they are accepted values for different elements and compounds and it's basically how much energy it takes to form these elements and compounds. So they are studied under what we call standard state. So they are all studied under the same conditions, which is just a control for, because if the temperature was different or if you were under different pressure conditions, things will change. Certain aspects of your experiment would change. So they do everything under standard state. So standard state conditions is defined as 1 atmosphere of pressure, 25 degrees C, and 1 molar if you are working in a solution. So that's standard state conditions. So all of our formation constants are studied at standard state. Okay, so any element that is in your table or is in a reaction is going to have a value of 0 for delta H of formation, okay? It doesn't take any energy to make, say, oxygen. Oxygen is just there. We don't have to do anything. Water, however, you need to combine 2 elements in order to make water, and that's going to either require energy or it's going to give off energy, so you're going to have a value for, say, water. You will not have a water for hydrogen by itself, oxygen by itself, aluminum by itself. Anything that's alone and is in its elemental state has a value of 0. And you'll see that in your table. In Appendix 2 of your book, there's really no page number. It's Table B. The page is like A-5, whatever. It's in the back of your book. That's where your quantities are. I will also give you a table that I've photocopied from the back of the book, but if you miss it or you misplace it or whatever, it's all in your book in the back. Okay, so these you're going to have to look up. They're in alphabetical order by element. The only thing that's a little tricky is that your water, H2O, you might look for it under hydrogen because it starts with H, but it's actually in the oxygen section. You also need to be careful about the state of matter. So in your table, you'll see, if you look under the oxygen section, there's water liquid, and then there's water gas, and then there's hydrogen peroxide, which looks a lot like water, and there's liquid and gas for that one too. So they're all kind of listed together, and they all have different delta H values. That's supposed to be an X. And so you just need to figure out, make sure that you pay attention to the state of matter when you are given a chemical reaction. So if it's gaseous water, it's going to have a certain tabulated value. If it's liquid water, it's going to have a different value. So just keep that in mind when you're looking stuff up. Okay, anyways, all you're going to do is look up these values, and you're going to take the products and add all the values up. And then you're going to take the reactants and add all the values up for all the reactants and subtract them. And that's it. So the math is very easy. It's just a matter of finding them and remembering that your products are on. So if you have a reaction, it goes reactants to products. Your products are listed second. So you sort of need to switch. You put the products first when you do this reaction, when you do this equation. Okay, whatever, enough talking. Okay, number 22. We are going to, the biggest mistake I see people make is they'll just write the values underneath each element or compound and then just do the subtraction. But you can't do that because it's products minus reactants, and here are your reactants and here are your products. So what I tell people to do is, if you're afraid you're going to do that, just reverse the reaction. So do this. 4NO plus 6H2O minus 4NH3 plus 5O2. Now, when you look up the values, you have this, and you can just write them right under it, and you're not going to make that mistake. Okay, so what I'm going to do is I'm going to look up my values in my table, and I'm just going to write. You need to write my values down. You need to bring down your stoichiometry. So I'm going to do this. 4 times. I looked at my value for NO in the table, and it's 91.3. My units are kilojoules per mole. And I'll put that in at the end, just because it gets really messy if I do it here. All right. Then I need to bring 6 down, and I multiply that by the amount for oxygen. For water, and it's gaseous water. So that is negative 241.8. Okay. There are my products. Now I need to do my reactants. Now remember, this is elemental, oxygen, so that value is just 0. So I'm going to do 4 times, and my value for NH3 is negative 45.9. Again, these values that I'm writing, I got right from that table. And I'm going to just say add 0, just so you know that I didn't forget oxygen. It's just 0 because it's elemental. Okay, just do the math. So you do 4 times 91, whatever, 6 times negative 2, 4, add them up. Don't forget your negative signs. Then you do the subtraction, and you get negative 902 kilojoules. That is your delta H. So I reversed the reaction. So I put these guys over this side, and I put these guys over this side, and then I just looked up the values in the table. I brought down the stoichiometry. Okay, this is elemental, so it's 0. And then I added up my products. I added up my reactants, and I did the subtraction, and that's my answer. So that's it. So I want you to do the same thing for 23, and then I will show you the answer. There is the answer for number 23. Check your numbers. Make sure you understand what you're doing. If you got these answers but your sign is different, you probably just need to flip your reaction. So there you go. And that is the end of week 2. So do your homework. If you have questions, bring them to class.